SpaceX just cranked up the power on their Raptor 4 engine by 43%, and NASA engineers are scratching their heads. While NASA's been busy with their lunar rocket, SpaceX has built an engine that pushes out 330 tons of thrust. That's more oomph than anything we've ever sent into space. But here's the kicker: this beast is cheaper and lighter than weaker engines. How'd they pull that off? Rocket engineers all know that more power usually means more stuff, more weight, and more money. SpaceX just tossed that rule out the window. What's their secret? And why is NASA hustling to catch up before Raptor 4 roars to life in 2028 for those Mars missions? Let's get into the engineering that's got everyone buzzing. So, how did SpaceX crack this puzzle when NASA was just adding more stuff to their engines? SpaceX went the other way. They started taking things out. Here's the twist nobody saw coming. Old-school rocket engines use tons of bolts and flanges, all those little metal bits that hold everything together. But those tiny parts? They're the weak spots. They leak, they crack, they break under pressure. SpaceX asked a simple question: what if we just welded everything together? Boom! 330 tons of thrust from an engine that's actually simpler than the old ones. But that's not all. Remember that 43% power boost? Get this, Raptor 1 weighed a hefty 2 tons. Raptor 2 dropped to 1.6 tons, which was better. Then came Raptor 3 at 1.5 tons. Now, Raptor 4 is even lighter and packs that extra 43% power. That's not how it's supposed to work. More power usually means more weight. It's like saying your sports car gets lighter as you pump up the horsepower. SpaceX didn't just bend the rules, they smashed them. Why does this matter? Starship uses 33 engines. If you shave off even half a ton per engine, you're looking at 16 tons less weight overall. That's a whole extra payload you get for free. Building rocket engines used to take ages. Raptor 1 took 11 days per engine. At that rate, SpaceX would need decades to build enough engines for those Mars missions. Raptor 2 got it down to 2 days, which is good, but still not fast enough for Elon's plans. Then bam! They got it down to 1 day per engine, start to finish. But wait, there's more. Raptor 3 is already showing signs of quicker builds, and early guesses say Raptor 4 could be built in hours instead of days. Think about that. NASA takes years to build one engine. SpaceX could crank out enough engines for a whole rocket in a week. The secret? That same less is more thing. Fewer parts mean faster builds, fewer steps mean fewer mistakes, and fewer mistakes mean faster production. Traditional rocket engines cost a fortune. NASA's RS-25? $146 million each, and they're one and done. Blue Origin's B4 is estimated to be around $20 to $30 million per engine, still crazy expensive. SpaceX's Raptor 2 already cut the cost to $1 to $2 million, a 90% drop. But Raptor 3? They're aiming for $600,000 per engine, and Raptor 4 might hit $500,000 or less. Let that sink in. SpaceX is making engines that are 300 times cheaper than NASA's, while also being more powerful and reusable. That's not just a step up, it's a total game changer. Raptor 4 is putting out 330 tons of thrust per engine. Multiply that by 33 engines on the Super Heavy booster, and you get almost 11,000 tons of total thrust. That's more than triple the Saturn V rocket that took people to the moon. We're talking about the most powerful rocket system ever built. But it gets wilder. Future versions could use 35 engines on the booster and 12 on the ship, pushing the total thrust past 11,500 tons. The ship alone would make over 3,000 tons of thrust, almost as much as the entire Saturn V. And remember, this is just one Starship. SpaceX wants to build hundreds of these. Here's a part of the story SpaceX probably doesn't want you to know: this almost didn't happen. Early Raptor engines had a major flaw: they were melting from the inside out. When you're burning methane and oxygen at super high pressure, you get temps that can melt steel. The engines were destroying their own cooling systems. SpaceX tried everything: more cooling lines, better materials, fancy heat shields. Nothing worked all the time. Then, they had a breakthrough. Instead of adding more cooling, they redesigned the whole engine to need less cooling. Raptor 3 got rid of the heat shield entirely. Raptor 4 takes it even further. The cooling is so good that these engines can fire over and over with little work needed. They could fly to Mars, land, take off, and fly back multiple times. SpaceX is rushing Raptor 4 for 2028 because that's when the Mars launch window opens. It only opens every 26 months, so you miss it, you wait. SpaceX has been planning for 2028 since day one of the Starship program. But here's what makes this mission different: it's not just about getting to Mars, it's about staying there. Raptor 4 can send 300 tons of stuff to Mars. That's enough to build whole habitats, power systems, and everything you need to live there in one trip. NASA's ideas involve dozens of launches over years just to send a few astronauts for a quick visit. SpaceX wants to send enough stuff to build cities in just a few flights. There's something SpaceX isn't saying about Raptor 4: all that power comes at a cost. As of May 2024, Raptor 3 had done over 300 test firings. That's 16,000 seconds of runtime. Each test costs hundreds of thousands of dollars in fuel, test stands, and analysis. Raptor 4 will need even more testing because it's more powerful. Why is SpaceX willing to spend that money? Because one engine failure on the way to Mars could kill everyone. There's no roadside assistance 100 million miles from Earth. A Starship can't carry enough fuel to reach Mars and back. But what if you could refuel in space? SpaceX wants to launch tanker Starships to orbit. Each one dumps its fuel into the Mars-bound ship until it has enough for the whole trip. This needs engines that can restart in space, fire dozens of times without problems, engines like Raptor 4. The first orbital refueling tests are planned for 2025. If they work, it's game on for Mars missions, moon bases, and asteroid mining. If they don't, the whole Mars plan gets pushed back. Elon Musk always says, the best part is no part. Sounds simple, but it's revolutionary. Old aerospace companies add backup systems for everything. SpaceX makes things reliable by getting rid of the things that can break. Can't have a bolt fail if there are no bolts. Can't have a flange leak if there are no flanges. Raptor 4 takes that idea to the max: fewer parts, fewer joints, fewer chances for things to go wrong. The result? An engine that's more powerful and more reliable than anything before it. Is SpaceX going too fast? Are they skipping steps that other companies think are important? When you're talking about people's lives on Mars, can you really afford to cut corners? NASA takes decades to build new engines. They test everything to death, use backup systems, and move slowly. SpaceX builds new engines in years. They test hard, break things, and try again quickly. It's a new way, but what will it cost? The answer will show if Raptor 4 is our ticket to becoming a multi-planet species or a warning about going too fast. Only time will tell which way is right, but we're about to find out. SpaceX just proved that more power doesn't have to mean more problems. They've changed the rules of rocket engineering, and NASA's trying to catch up. By 2028, these Raptor 4 engines could be carrying the first Mars colonists. Think about it. Your kids might live in a world where going to Mars is normal and space is our new backyard. Is SpaceX going too fast, or is everyone else too slow? SpaceX did something wild. Every rocket for 60 years used dome fuel tank. SpaceX's test tank 17 has no dome, just a flat 90 degrees weld where the dome should be at all. This changes everything, like no carbon dioxide purging faster, manufacturing cheaper launches. But how does a domeless tank handle 7,000 tons of engine force without exploding? It's making every aerospace company copy this design. SpaceX didn't just prove rockets, they rewrote their rules. Tank is covered in thick frost, revealing something that should be impossible. For 60 years, every rocket fuel tank had a curved dome at the bottom, but instead, they found a brutal 90 degrees weld. How is this possible? Why is their entire aerospace industry trying to understand what SpaceX just accomplished? Every aerospace engineering textbook talks about how curved surfaces distributed pressure better than flat surfaces. SpaceX's engineers know this rule. They follow this rule for years, then they discover that the dome wasn't solving the pressure problem. It was creating an entirely different problem. Traditional dome tanks have hidden spaces where gas can accumulate. So every rocket needs carbon dioxide purging system. What if you could eliminate the purging entirely? Instead of managing the gas buildup problem, they eliminated the spaces where gas could build up. No dome equals no hidden pockets equals no purging. Does this create the original pressure problem?